Hey guys, the next thing that we're going to talk about is the sun. So, just some measurables, if you will. So, the physical properties of the sun, the radius is about 700,000 kilometers. You do not need to memorize any of this stuff. The mass is 2 times 10 to the 30 kilograms, so it's very big. The density is 1,400 kilograms per cubic meter. The rotation is differential. In other words, it varies depending on where in it you are. Surface temperature is about 5,800 degrees Kelvin. Notice that's the surface temperature, not the core temperature. And the apparent surface of the sun is called the photosphere. So this is a filtered image of the sun showing a bunch of different features. You have some sunspots on here, which are the dark spots, and then you have the corona going around the outside. And then the photosphere shows up as this dark line on the edge. So as far as the interior structure goes, you have the core is where nuclear fusion happens. Nuclear fusion is where we fuse hydrogen into helium. And that's what really powers the sun and all the rest of the stars. Outside of that, we have the radiation zone and then the convection zone. And then we have smaller layers, the photosphere, chromosphere, transition zone. And then corona is very, very, very large. So some other physical properties, the luminosity is the total energy radiated by the sun. It can be calculated from the fraction of that energy that reaches the Earth. The solar constant is the amount of the sun's energy reaches the Earth, which is about 1,400 watts per square meter. You need the solar constant in order to calculate the total luminosity of the sun. The total luminosity is about 4 times 10 to the 26 watts, which is the equivalent of 10 billion 1 megaton nuclear bombs going off per second. So just a ton of energy. And this basically shows how they kind of calculate the luminosity. So if we look here and we calculate the amount of energy hitting the Earth, then we can extrapolate that to the amount of energy that's being put out by the sun in every direction. As far as mathematical models are consistent with observation and physical principles, provide information about the sun's interior. Basically, with the sun, we have two main forces going on here. We have pressure from nuclear fusion, so that's thermal pressure or heat pressure. And then we have gravity pulling in, and those two forces are in equilibrium. And that's why the sun basically stays, pretty constant as far as the amount of energy that it's putting out. Let's see. All right. So in the radiation zone, basically, as it sounds like, radiation occurs. So the energy from the core is radiated out from the core to the convection zone. The convection zone, as you can see here, has all these, just like convection in the Earth or anywhere else, has all these circular currents going on, so where the heat is taken from there, and you have a heat imbalance here that has to get equaled out by the time you get to the photosphere. So that's what happens in the convection area. So radiation zone radiates the energy away. Convection zone has convection currents that basically do the same thing. These are the tops of the convection cells. You're going to see in the video that I posted for you that these are actually constantly churning. Very, very cool. As much as this picture looks kind of neat, the video is that much better. A lot of the information that we get from what we call SOHO, which is the Solar and Heliospheric Observatory, which orbits at Earth's L1 point outside the magnetosphere, and has a whole bunch of different instruments. Magnetic field, vibrations, and UV emissions are all measured all the time. The L1 point is called the Lagrange point. And if you want to look into that, it's actually a pretty cool thing if you want to look it up on your own. It's basically where you can put a satellite in orbit and it will just stay there without any propellant or anything. The sun's atmosphere, We do spectral analysis that can tell us what elements are present, and notice it shows here that 67 different elements are present in the sun's spectrum. So lots of stuff out there. Some of it is more important than others as far as like what's really going on inside. The cooler chromosphere is above the photosphere. Difficult to see, but during a solar eclipse, you can see some different features that you wouldn't normally be able to see. Here, you can see the corona going out around there. You can see solar flares around the edge, all sorts of features. Small solar storms in the chromosphere emit what we call spicules. That's what these things are called. And these spicules will end up forming loops. We'll talk more about them in a second. And the solar corona can be seen during an eclipse if both the photosphere and the chromosphere are blocked. Then we get to the transition zone. This is really interesting because if you look at this little graph here, this shows, so this is the distance from the sun as you go out, and here's the temperature. And what it shows is that the temperature actually starts going down as you get further away from the sun, which is what you would expect. And then you get to this transition zone, and the temperature skyrockets up here as you're getting further away. So you have this area where you're getting farther away from the sun, but the temperature is actually increasing a lot. That's the transition zone, and then you get to the corona and kind of levels out a little bit. The video will also talk about that. These are sunspots. This is what they look like up close. So these are darker, relatively cooler areas on the surface of the sun. And here's what they look like if you just take a picture of them with like a more normal imaging. And those sunspots are in pairs, and you have one that's a magnetic north and one that's a magnetic south. And these loops that we call here are what we call prominences. So these are loops of plasma. And if this loop breaks or pops, then you can get a coronal mass ejection or a solar storm. Like I said, the video will show you these and show you some very cool images to go along with that. This is why we think they happen, the magnetic field lines, because the sun is rotating at different speeds. We think that these magnetic field lines get like kind of twisted and distorted, and then every once in a while they'll make these loops, and we think that's what creates a lot of the stuff: the sunspots, the prominences, the solar flares, coronal mass ejections, all that stuff. And these sunspots occur in an 11-year cycle, where you have peaks and valleys. So this is just kind of showing that data over time. But really, you have positive and negative, so it's actually a 22-year cycle. Don't worry about that. Here's a picture showing you a prominence here that's looks like it's about to rupture. And here shows you a more detailed, higher definition picture there. So a solar flare is a large explosion on the sun's surface, emitting similar amount of energy to a prominence, but in seconds or minutes rather than days or weeks. And a coronal mass ejection occurs when that large bubble detaches from the sun and escapes off into space. So this actually sends mass from the sun flying off into space. Tons of energy goes with it. And then there's always solar wind that's flying through space. Lots of electrons and particles that are flying away, bringing away lots of energy. Sorry. And I think that's about it as far as what we really need to cover. We kind of need to move on here, and I know you guys have the video to watch. So the video really goes through most of that stuff, shows you much, much better detail, and you get to visualize it. So that's why I kind of flew through that presentation. But so enjoy the video, answer the questions, and post the answers.